we're now going to take what we learned about potential functions and conservative vector fields, and we're going to now develop something called the fundamental theorem of line integrals, which are going to make the job of actually finding line integrals a lot easier. This is going to be very important for work in physics and instead of engineering and the like. So what we need to do is we need to start talking about the kinds of curves that we're going to be seeing inside of our vector fields and the kinds of regions that we're going to be integrating over. So we'll start out with this idea of what's called a simple and closed curve. So a curve C is closed, and if there's a parametrization R of t, a less than or equal to t less than or equal to b of c such that the parametrization traverses the curve exactly once, and R of a equals R of b. Basically what that means is we look here, this is a closed curve. Assuming that we only pass over, we go from A to B, okay, so we only do that once, right, and our beginning point is the same as our ending point. You can see this curve right here is not closed, okay, because R of A does not equal R of B. In addition, say for example, we had a trigonometric function in which we actually went around the circle twice, for example. That in fact would also not be closed because it would not traverse the curve exactly once, it would have traversed it twice. Our next definition is something called a simple curve. So a simple curve is a curve that does not cross over itself. So we can actually see that we have something that is like simple but not closed. This one doesn't cross over itself. So it's simple but it's not closed. We can have a closed curve like this one here where we're crossing over the curve at a particular point, and so this is closed but it's not simple. Or we could also have a closed and simple curve, and these are going to become very important for when we start talking about the fundamental theorem of line integrals. Next, we have something called connected regions. Note now we're actually moving over to regions. And so a connected region is one where we have any 2 points P and Q and D. We can construct a path from P to Q where the trace is entirely inside of D. Now the trace is just a drawing over the path. So like let's imagine we have P, imagine we have Q. Clearly this path from P to Q, that's inside of the region. We could have this as being P, we could have this as being Q. So we can imagine that's moving, okay? That's inside of the region. We can in fact have P and Q be the same points, and we can imagine a couple of different paths that go from P to Q. Okay, something along those lines. So this is a connected region. Similarly, we have this is a connected region. You can tell it's connected. There's no holes at all inside of this region. So if this was P, this was Q. But in this region, the change here is that the region is actually split. So if we put P here in the first part of our region and Q in the second part of our region, there's no way to actually create a curve, right? Any curve that we took from P to Q would actually necessarily have pieces that are not in the region. So this actually means that the region is not connected, right? That's what makes the region not connected. So you can kind of see that's kind of how we're talking about what it means to be a connected region. And then we can have something called a simply connected region. So a region is simply connected if D is connected and any closed curve C inside of D can be shrunk continuously to a point while staying entirely inside of D. So in 2 dimensions, a simply connected region has no holes. And so to give you an idea, that triangle region, that's simply connected. That's a simply connected region. Choose any path. You can shrink the path, right? We're going to remain inside of the region. This is not a simply connected region. Let's imagine it's got some holes in it. And so what I want you to imagine is we've got P, okay, and we have a closed curve for P. Imagine then that you start shrinking that curve. And we start shrinking the curve, okay? And we shrink the curve, and what you're going to see here is now we can't actually shrink the curve through the hole, right? There's that hole, and so we can't shrink the curve for P through the hole. So consequently, this is not simply connected. It's connected, but it's not simply connected. So consequently, we've got these definitions, right? We've got the idea of a simple closed curve. That's going to be important. Basically, the idea is that the curve, right, it begins and ends at the same point, traverses only once, okay, and doesn't cross over itself. And then we have the idea of a simply connected region. That's basically a region in 2 dimensions with no holes. Same thing, it's basically like, if you kind of think in a volume, it's got no bubbles, right? You've got a volume, it's got no bubbles in the volume, right? No pockets inside of that volume. And that's another way to think about a simply connected region, but in 3 dimensions. Now what we're going to do is we're going to look at something called the fundamental theorem of line integrals, which, if what we were working with is conservative vector fields, can save us an incredible amount of time and energy and can make things a lot simpler. It just ends up being a very powerful theorem for our use, especially if we're working inside of physics or inside of engineering or in kind of electromagnetism, anything like that. So the fundamental theorem of line integrals says, let C be a piecewise smooth curve with parametrization R of t, a less than or equal to t less than or equal to b, and let f be a function of 2 or 3 variables with first order partial derivatives that exist in continuous on C. Then we've got the integral on C of del f dot dr is going to equal f of r of b minus f of r of a. Okay? Now, where this ends up becoming really important, well, there's 2 things. Let's actually first start with, this is basically the fundamental theorem of calculus. Okay? If we have this parametrization R of t, then del f, okay, del f is basically just equal to del f dot dr is going to end up equaling essentially d dt of f of r of t r prime of t, okay? And then if we take the integral of that along the curve, right, we're going to get f of, we're going to d dt, f of r of t, r prime of t, dt, and that's essentially going to be just f of r of t, and our curve is going to be actually evaluated from a to b. So this is going to be from a to b, okay, which is just going to end up being f of r of b minus f of r of a. So super handy, right? Okay, like basically this is by the fundamental theorem of calculus, this piece here. By calculus, the fundamental theorem of calculus. So where this is going to come in really handy is that if we have a conservative vector field, we know something about del f dot dr. We know if f is conservative, okay, then del f is equal to f, our conservative vector field, okay, all right, and so consequently, if we can retrieve f, if we can get back f, right, okay, and f, remember, note from our earlier conversation, f is going to be our potential function phi. Okay, then we can use the fundamental theorem of line integrals. So basically what we're going to do is we're actually going to look at whatever the field is that we're going to be working on. Okay, we're going to be looking at the field that we're working on, and we're going to make a determination as to whether or not that field is conservative. If that field is conservative, then what I'm going to get here is I'm going to get this integral, the integral C of f, my conservative vector field dot dr, is then just going to equal f of r of a minus f of r of b. So I actually have a much simpler way of determining f dot dr rather than going through the whole process of solving for my line integral. Okay, so this, we call that the easy way. Okay, go out and find that potential function. Once we found the potential function, then I can go out and I can actually solve for, solve my line integral just by using the fundamental theorem. So let's suppose that we have the, we want to calculate the line integral of f dot dr, where our vector field f is equal to 2x ln y, x squared y plus z squared, and 2yz. And C is the curve R of t equals t squared t, 1 less than or equal to t less than or equal to e. Now, if I were to go out and calculate the line integral f dot dr directly, this is actually kind of involved and a little bit of a problem, a little bit hard. But if I happen to have a conservative vector field, then what I'm going to be able to do is I'm going to actually be able to go in and use the fundamental theorem of line integrals. So let's go calculate whether or not this is in fact a conservative vector field. So I've got phi x is going to end up, or excuse me, p is 2x ln y. So py is going to equal 2x over y, and pz is going to equal 0. Okay? Qx is going to equal 2x over y, and qz is going to equal 2z. And then rx is going to equal 0, and ry, excuse me, is going to equal 2z. Notice py equals qx, pz equals rx, and qz equals ry. So py equals qx, pz equals rx, qz equals ry. So f is conservative. Now what I'm going to need to do is I'm going to need to go in here, and I'm going to go in and I'm going to find my potential function phi. So remember, I'm going to take the integral, start with the integral of, so I'm going to find phi, or we'll call it f too. That's in our fundamental theorem of line integrals. We're looking for phi. So 2x ln y dx, and this is going to end up equaling x squared ln y plus some function g of yz. Then I'll take del y of x squared ln y plus g of yz. And that's going to end up equaling x squared over y plus, we'll call this g with respect to y. I'm now going to compare that to phi of y. So that's going to be x squared over y plus gy is equal to x squared over y plus z squared. Those will cancel. We get that gy is going to equal z squared. Now I'm going to integrate with respect to y. So I'm going to integrate z squared dy. And that's going to end up equaling z squared y plus, and this will be some h of z. And finally, what I'll need to do is I'll need to take the derivative z squared of z squared y plus h of z. And I'm going to take del z, so the partial with respect to z. That gives me 2zy plus h prime of z. I'll now return because I need to compare that to phi of z, or my r. So that's 2yz. So 2yz equals 2yz plus h prime of z. Okay. Take the integral, both sides. Well, first notice that goes away, so we get h prime of z equals 0. So we'll integrate. This is going to end up just giving me a c. As I stated before, we don't actually need the constant. So because, well, we'll integrate this. This actually gives me z dz, 0 to z equals h of z. And this is just going to equal some constant. But the constant drops off when we actually use our function. We don't need to use the constant. So we're going to get rid of that, and we're just going to have x squared ln y plus z squared y, excuse me, or yz squared. So x squared, so our phi, or our f, in this case, the function we're looking for, is going to equal x squared ln y, right, this piece right over here, plus yz squared, and then this is just the constant, but the constant will just drop off. So we'll let f equal this, x squared ln y plus yz squared. Okay? So that's our function. cool, right? The reason why this is cool is because now I actually know that this integral, the integral of f dot dr, is going to equal f of r of a minus f of r of b, or excuse me, r of b minus r of a, excuse me. So we know that here is our parametrization, t squared tt, and t greater than or equal to 1, less than or equal to e. So I'm going to rewrite this down here. So t squared t, and we're going to have t greater than or equal to 1, less than or equal to e. So my x values for b are going to be e squared e, right? So that's going to end up being b, or r of b rather. And then r of a is going to equal 1, 1, and 1. So now I'll just go in and evaluate. I'll plug in e squared e. Okay, so f of e squared e minus f of 1, 1, 1 is going to equal e to the 4th ln e plus e cubed minus, and this is going to zero out, so this is going to be 1 times 0 plus 1, so minus 1, which is equal to e to the 4th plus e cubed minus 1. Which ends up being, I know it seems like a lot, but it ends up being a lot easier and a lot simpler than actually going out and finding the line integral. Okay, so since we had the conservative vector field, we could go out and find our potential function, and then once I found my potential function, all I needed to do is evaluate my parameterization at its endpoints, plug those into the function, and then evaluate that. Let's take a look at another example. Let's suppose we have the integral, the line integral f dot dr for f of xyz equal to 3x squared z I plus z squared j plus x squared plus 2yzk along r of t equals the natural log of t over 2, natural log of 2i plus t to the 3/2 j plus t cosine pi t for t greater than or equal to 1 and less than or equal to 4. Now, f dot dr using a traditional line integral is going to be prohibitively difficult. It's going to be hard. But we could possibly use the fundamental theorem of line integrals assuming that f is a conservative vector field. So what I'm going to do is I'm actually going to go out and figure that out. So I'm going to start out, I'm going to have p, here's my p. So py is going to end up equaling 0, and pz is going to end up equaling 3x squared. qx is going to end up equaling 0, and qz is going to end up equaling 2z. And then rx is going to end up equaling 3x squared, and ry is going to end up equaling 2z. Notice pz equals rx, py equals qx, and qz equals ry. Thus f is conservative. So we have a conservative vector field. Very nice. Okay? So I don't actually have to go out and calculate the line integral by hand. Instead, I just need to find a potential function. So I'm going to start out with 3x squared z I. So that means I'm going to find the integral of 3x squared z dx, and that's going to then be x cubed z plus some function g of yz. Then I'm going to go in, I'm going to take its derivative with respect to y. So del y of x cubed z plus g of yz is going to end up equaling 0 plus g of y. Okay? And so I'll compare that now to phi of y. So phi of y is over here at z squared. Okay? So phi of y equals z squared, and it equals 0 plus gy. Thus, gy equals z squared. We're now going to add this on to x cubed z. So we now have that our function f is going to equal x cubed z plus yz squared plus h of z. And now I'm going to take the derivative with respect to z. That's going to give me x cubed z plus yz squared plus h of z. And that ends up equaling x cubed plus 2zy plus h prime of z. Now, I can go in and I can say, okay, well, let's compare that against my function r. That's x cubed plus 2yz. So we've got x cubed plus 2yz is equal to x cubed plus 2yz plus h prime of z. So these cancel. We end up with h prime of z equals 0. If we integrate, just for the sake of completion, h prime of z dz equal to 0 dz. We get just some constant. So our h of z is a constant, but we can drop off the constant. So our function f, okay, f of x, y, z is equal to x cubed y. Okay, it's gonna be this piece right here, or x cubed z, excuse me, x cubed z plus yz squared. And that is our potential function and the one that we're going to use for the fundamental theorem of line integrals. So now I'm just going to bring down my r of t. So I got r of t is equal to ln t over ln 2, comma t to the 3/2, comma t cosine pi t. And we're going to evaluate that from 1 less than or equal to t less than or equal to 4. So r of b, my endpoint here for 4, is going to equal the natural log of 4 over the natural log of 2, which just equals, okay, 2. 4 to the 3/2, we've got, this is going to end up equaling 8. And then 4 times cosine 4 pi, so that's 4. 2, 8, and 4. R of a, which equals r of 1 now, is then going to equal, that's the natural log of 1 over the natural log of 2, so that's 0. And then 1, and this is going to end up being negative 1, because cosine of pi is negative 1 times 1, that's negative 1. So those are our endpoints. So now, using the fundamental theorem of line integrals, what we get is we get that the integral of c of f dot dr is equal to f of 284 minus f of 0, 1, negative 1. And that equals 2 cubed times 4 plus 8 times 4 squared minus, and this is 0 plus 1. 159. And we're done. And you can see, actually, do those line integrals a couple of times, and you'll see that utilizing this method, if we have a conservative vector field, makes life a lot easier. So here's some key theoretical results that we get from the fundamental theorem of line integrals and conservative vector fields. The first is that we have a path independence for the conservative fields. Remember from that fundamental theorem of line integrals that what we got from the line integral over c of f dot dr, okay, was equal to f of r of b minus f of r of a. So that was the result that we got. Well, this actually does indicate for us that this is independent of path. We don't actually care about the parametrization at all. We just need to know its endpoints. And we in fact did that. So this is, right, this is endpoint 1. Okay, and here's endpoint 2. And as long as we know those endpoints and we know our potential function, we don't actually need to know the path at all. And this is true for all conservative vector fields, because for every consecutive vector field, we can find f, right? So consequently, if we know that we have a conservative vector field, then we know that f is then going to be independent of path, all right? And that comes in from the fundamental theorem of line integrals. Consequently, if we have f as a continuous vector field and is independent of path, and the domain of D is open and connected. So this is actually also really important, that second point, right? It needs to be open and connected, all right? Then f is conservative, right? So as long as we don't have any holes inside of the field, or we don't have any bubbles inside of a three-dimensional field, what we have is we end up having a conservative vector field as long as it's independent of path. From a practical perspective, this only matters in so much as we know that if we have a conservative vector field, we can use the fundamental theorem of line integrals, okay? And really, most of the time, you're just going to utilize that test for a conservative vector field by taking its mixed partials and showing that they're all equal to each other. And so, consequently, like this second piece here, that path independence for conservative fields, it really only plays a role in kind of like theoretical mathematics, right? We know that something's independent of path. We know that it's open and connected. Oh, hence, voila, I have a conservative vector field. For our purposes, most of what we're going to be doing is we're going to be determining if we have a conservative vector field, and then we're going to use the fact that it's independent of path in order to give us some some interesting information. So let's consider a situation where this might come in handy. Let's suppose that I have f of xy, and that's equal to 2xy squared and 2x squared y, and it's a force field. And suppose that we have a particle that begins its motion at the origin and ends its movement at any point in a plane that is not on the x-axis or the y-axis. And then furthermore, the particle's motion can be modeled with a smooth parametrization. So we want to show that f does positive work on the particle. Well, since we don't know the path, we've got a problem. Unless this is a conservative vector field. So let's take a look and let's see if it actually is a conservative vector field. So we're going to take, we're going to have q of y, and that's going to end up being equal to 4xy. And we're going to have, p of y, and we're going to have q of x, and that's going to end up being 4xy as well. P of y equals q of x, f is conservative. We'll just abbreviate that, f is conservative. So now what I want to do is I want to go out and find my potential function. So I've got my integral. Well, first things first. Before I go anywhere, the particle is now inside of a conservative vector field. So the work done on the particle, that f dot dr, is going to be independent, completely independent of the path that it travels. Basically, everything's going to even out because we're looking at a conservative vector field. So what we're going to do now is we're just going to go out and find that potential function and then calculate the work done for any point along this graph, okay? So I'm going to start out with the integral of 2xy squared dx. This is going to equal x squared y squared plus, we'll call this h of y. We'll take delta y of x squared y squared plus h of y. And that'll equal 2x squared y plus h prime of y. Okay? And then we'll compare that to compare that to q. And so 2x squared y plus h prime of y equals 2x squared y. So h prime of y is just equal to 0. If you take the integral of that, we've already seen that a couple of times, that in fact, what we get is we just get a constant. So this drops off, the constant drops off. So my f is equal to x squared y squared. That's my function. Now, I just need to calculate this at the endpoints. So we're going to have one endpoint, endpoint 1, at 0, 0. That starts at the origin. And then we'll choose another endpoint. We'll call that another endpoint AB. That's my second endpoint. So by the fundamental theorem of line integrals, FTLI, we'll get f of 0, 0 minus f of AB, and that equals the work, which is f dot dr, along any path. Doesn't matter what the path is. So this ends up equaling, that's backwards, should be f of AB minus f of 0, 0. And that equals then a squared b squared minus 0, which equals just a squared b squared. And that is the amount of work done on this vector field traveling from the origin to any point on the vector field, as long as it's not on the x or y axis. So let's take a look. It says, show that f does positive work on the particle. Okay? So we got smooth parametrization, and show that this is in fact positive. Well, a squared b squared is going to be greater than 0 for all a and b, as long as we're in the real a and b belonging to the reals. So the integral, the line integral f dot dr, the work done, is going to be greater than 0 for all a, b. And there we are. All right, so the fact that we actually are working in a conservative vector field, okay, makes it pretty easy to kind of figure out, like, say, for example, work done, right, on that field, right, because all we need to do is we just need to figure out what the potential function is. Once we pull that potential function, then that will go out and we can then just plug in our endpoints into the potential function, and that will give us the amount of work done. All right, so it took us a little bit of work to get here, but now that we're here with, and we've kind of completed our fundamental theorem of line integrals, what we can see is we can see a really powerful tool for making our work a lot easier. Okay, for making our work a lot easier, like kind of expanding what we can do, cutting down on our computation, which is a huge part of doing mathematics, and also, you know, kind of thinking about special classes of objects and how doing math on special classes of objects can really, like, again, be simplified. So when we're looking at a conservative vector field, right, what we want to remember is that we can calculate the line integrals on that conservative vector field independent of paths using the fundamental theorem of line integrals. So what we want to do first, okay, before we do anything, is determine whether or not we're working with a conservative vector field. If we actually are, then what we can do then is utilize that fundamental theorem, make our lives a lot easier, go find a potential function, and then calculate the value of the potential function on the endpoints of our path. Okay? And that just makes things so much easier. That's the whole point of doing the fundamental theorem. Okay? It took a little machinery, but now that we're here, we've got something that actually can make things a lot easier.